special meeting. It's a special meeting, you know, when you have somebody to introduce the person doing the introduction, right? So that's the case tonight. So Jerry, if you come up, and Eric, if you change the slide, please.
1 second here. I need to stop sharing and share over here. There you go.
Are we ready? Well, I am here tonight to introduce the introducer. So introducing tonight's guest will be Rebecca Lewis Merrill. For those of you that may not know, she was our first Striking Sparks Telescope awardee in 2012. She was in the 8th grade at Sebastian Cuesta Elementary School. And yeah, she got her telescope. She was very active in the club. And 3 years after she got her telescope, we made her newsletter editor. So she's been the editor of our Valley Skies ever since, even after she left town, headed to UCLA to continue her education. 2020, she earned her Bachelor of Science degree in astrophysics. She stuck around at UCLA since then. She's now working on her PhD with the UCLA Galactic Center Group. The director of that group, Andrea Getz, won the Nobel Prize in 2020 for demonstrating unequivocally that the center of our galaxy contains a supermassive black hole, one that has a mass of about 4 million suns. She has 2 papers published right now, and 2 years ago, she was our guest speaker here at this meeting. And so I'm going to turn things over to Rebecca Lewis Merrill.
Thank you. All right. So it's my pleasure tonight to introduce my PhD advisor, Dr. Tuan Do. He got his undergraduate degrees in physics and astronomy at UC Berkeley in 2004 and his PhD at UCLA in 2010. After being a postdoc at UC Irvine and a Dunlap Fellow at the Dunlap Institute in Toronto, he returned to UCLA in 2015 as a research scientist, and he joined the faculty at UCLA in the physics and astronomy department in 2020. So as far as I know, he is both the deputy director of the Galactic Center Group and the PI of the Astrophysics Data Lab at UCLA. I met Tuan back in 2019 when I was an undergraduate, and I have been privileged to work with Tuan as an undergrad, as a post-baccalaureate researcher, and now as a grad student. He is honestly one of the best scientists, advisors, and teachers that I know, and I'm really glad that you all get to meet him tonight. So take it away, Tuan.
Thanks, Rebecca. That's really nice. Should I share my screen now?
Yeah, go ahead and share.
Okay. For my video point of view, I'm seeing like a table, so I can't see anybody. But if people would like to ask questions or do any discussion. Oh, okay, now I can see folks. Hello, everybody. Feel free to jump in. It's totally fine. I like having discussions. It's a little bit hard over Zoom, but feel free. Okay, so I'm gonna try to share my screen now.
I'll move this over here, guys.
Are you able to see the slide now?
Uh-huh.
Okay, great. Thanks. So thank you very much for the invitation. I'm wish I could be there in person, but I'd like to talk today about some of the work that our group has been doing. And in particular, I'd like to talk about how we can use our supermassive black hole at the center of our galaxy to study fundamental physics, meaning like how the universe works. So to begin with, though, I'd like to introduce the group a little bit. As folks have introduced, this is Andrea Guez. She's the director of the Galactic Center Group. This is a group photo we took a few years ago on top of a mountain called Mauna Kea, which is on top of the Big Island in Hawaii. Behind us, this giant white thing is the Keck Observatory. And then actually over here, the silver observatory is also, it's the Subaru Observatory. Anyway, the group is fairly large, but I'd like to highlight two of my grad students. One, Rebecca, of course, who you know very well, and then another student is Rory Bentley, who's going to defend pretty soon, actually, next month, his PhD. Okay, let's see. So today I want to talk about two big questions that we have in terms of our research. One is general relativity the correct description for supermassive black holes? And then the second is whether the fundamental constants of nature are really constant. So these two questions are related in the sense that they test the limits of the physics that we know today. Why do we care? Actually, before I talk in detail now about the physics part, let me introduce a little bit the Galactic Center itself. So you're all probably very familiar with this kind of view of the night sky. This is the Milky Way, and then if you follow Sagittarius, the teapot, it looks at the kind of part of the sky that is pretty blank. But if you look at the sky in the infrared, which is what this is now, you can see that actually it's the brightest point in the whole Milky Way because there's so many stars. And as we keep zooming in, we're using more and more sophisticated telescopes. This is the Hubble Space Telescope now. And then as we zoom in more, this is, by the way, our very first James Webb Space Telescope image of the center of our galaxy. And then we're going to keep zooming. This is the star cluster at the very center of our galaxy. And so as we get to the very, very center, you'll start seeing that the stars. Oh, so now we're going to get to this picture now comes from adaptive optics, which is from that giant telescope that we were standing in front of previously. I'll talk a little bit more about that further. And so let's keep going. And then if you go to the very, very middle and you look at the stars over time, you'll see that they move actually. And so this is what we do every year is we go back to the telescope and we take pictures of the sky, and then we can watch these stars move. And so the motions of those stars is what led to the discovery and the proof that there's a supermassive black hole at the center of our galaxy. And this, as was mentioned, led to the Nobel Prize in Physics in 2020, given to three folks, Roger Penrose, Reinhard Genzel, and Andrea Guez. They shared this prize for both the theory and then the discovery of the black hole at the center. So let me just play the video again of the stars going around because it's always wild. Actually, I work on this all the time, but it's kind of amazing that these stars, you can see the time here, are moving around a supermassive black hole. And the star that is the most interesting for us is this one, which is we call SO2, and it passes by the black hole. It has an orbital period of just 16 years around the black hole, and it passes by the black hole at closest approach at about 100 AU. So kind of like the scale of our solar system-ish is if you think about if our sun was a supermassive black hole, SO2 gets close to the closest it gets is sort of like outside the orbit of Pluto. Okay, so now that this the black hole has been discovered at the galactic center, the supermassive black hole, what are our next goals? And the goal really is to try to test physics itself using the supermassive black hole. And this first question I want to ask is general relativity the correct description for a supermassive black hole? I really like this cartoon. This cartoon has Einstein saying, we need to change space and time to make things work. And then somebody off the screen says, that's your solution to everything. And actually, that's literally true, which is that if general relativity, which is our best model right now of gravity, is correct, then it should apply to all things everywhere in the universe all the time. And so that means that gravity should work the same way on Earth, the sun, and right next to the supermassive black hole at the center of our galaxy. But we know from lots of observations now that we don't understand vast parts of the universe, actually. So our best models of physics, we know are incomplete. And the reason we know that's incomplete is that they don't predict the majority of the universe, which turns out to be made of something we arbitrarily call dark matter and something we arbitrarily call dark energy. The reason we call them dark matter and dark energy is that they don't really interact with light at all. And but together they make up 95% of the energy density of the universe. So we have a huge gap in our understanding of what makes up our universe. We know a ton about what makes up the Earth and us, and that's what the atom, these atoms part of this is. And that is really great. And a lot of physics has been really wonderful at explaining this. But what we want to know about the rest of the universe is how what the new physics are essentially. And so how do we figure out what this new physics is? Part of the way we do it is to think about areas of physics or areas of the universe or parameter space that we haven't tested. What do I mean by this? Is that let's look at this plot. This is a little bit complicated plot, but basically you can think of the x-axis here as the mass of an object, and then the y-axis as the gravitational potential, meaning how strong the gravity is. So Earth lives here. So we have Earth is a fairly small planet in the big scheme of things in the universe. It has enough gravity to keep us on the planet, but it's not very much gravity, right? But Earth, of course, is where we can test models of physics extremely precisely. We can build laboratory experiments, etc. Okay, we can go to other parts of the solar system, like Mercury. So Mercury feels the effects of general relativity around the sun because it's so close to the sun. We can use things like how light deflects around the sun to test general relativity there. We can use pulsars, which are these stars that are at the end stages of stellar evolution, where you have a very compact object that spins really fast. But this is kind of the limit to the mass. So as we said earlier, the mass of the black hole at the center of our galaxy is 4 million times the mass of our sun. So we're all the way out here in the x-axis. And because we are getting really close to the black hole, this 100 AU, that means that actually these stars feel really strong gravity. And so what it's nice is that we can test physics in this kind of parameter space, so that it may be like physics that are not showing up on the scale of the Earth might show up next to supermassive black holes. I would like to say also, by the way, you can't get infinitely high gravitational potential, because then you are on the surface of the black hole itself. So that's what this red line is. And so like gravitational waves, which are when two black holes kind of merge, can test this kind of space. But the gravitational waves that you've heard about are from black holes that are fairly small. The black hole at the galactic center is much, much more massive. So anyway, this is kind of saying about why we are so excited about having this laboratory right next to our neighborhood, basically, to test general relativity. And the thing that's exciting was that we were able to do this for the first time, to test general relativity for the first time at the Galactic Center in 2018. And so I want to go over a little bit how we did it. And this will help explain also what is coming next. And so in 2018 was when the star SO2 that I was talking about made its closest approach to the supermassive black hole. And so at that time, we can measure something called the gravitational redshift. Okay, so before I talk about gravitational redshift, I want to do a brief review of redshift in general. So there's this idea of a Doppler shift. We mentioned like if this is a star, let's say this is SO2, and this is the Earth, we're looking at it. If the star is moving away from us, the light of the star is going to be slightly redder. And so that's what we mean by redshift. And if the star is moving towards us, the light becomes slightly bluer. And so by measuring the amount that the light is shifted, we can basically determine the velocity of the star. So how fast is it moving away or towards us? Okay, so this effect always happens. It doesn't need to be next to a black hole. This is a completely Newtonian kind of effect. However, there's an extra effect when you're next to a source that has a lot of gravity, which is the gravitational redshift. And this happens when a star is in this strong gravitational potential. What happens is the light from the star that's reaching us, it loses energy actually. And this loss of energy translates to the light becoming redder. So basically the light's wavelength kind of gets stretched out, and that makes it redder. And to us, that looks like the star is moving away from us faster than it should be, right? So because it's like adding an extra redshift. And so here's a little video that is trying to demonstrate this. So we're going to look at in this video on the top and the bottom, on x-axis it's time, and then on the y-axis up here is the velocity that the star is moving away from us. Now this is in kilometers per second. And so let's see, I'll start this movie. So you can see the star. This is supposed to demonstrate that this is the black hole and this little divot, by the way. So as the star gets really, really close to the black hole, you see how it in the picture it gets a little bit redder. And that's because it's approaching the black hole kind of right here in where 2018 is. And if we subtract, so this velocity curve is the velocity of the star, so the motion of the star, which includes both general relativity and non-general relativity effects. But if we subtract all the effects of non-general relativity, you get like this bump here. So what's happening here is it's saying that in 2018, we would expect the star's velocity to jump more than it should if it's the model that's predicted by Kepler and Newton, so not Einstein models. Okay, this kind of sets you up for this experiment. So this is what we're trying to detect in 2018 from this star, SO2. So what do we need to do to actually do this? It turns out you need all of the data that you took before. So this data that started actually in 1995. So that's the first data set that Professor Rodriguez started collecting at Keck. And the reason for this is that you need to know the Keplerian orbit extremely well if you want to know deviations in the orbit, right? And so that all of that data was really necessary. So in fact, if you think about this experiment, because it started in 1995, 1995 plus 16 years is around 2002. So actually, SO2 went through closest approach more than once within our observation time. But the problem was that in 2002, we didn't know the orbit of SO2 well enough to see the effect of general relativity. And so 2018, we knew well enough that we should be able to detect it. Okay, so there were 3 important events that we needed to measure in 2018. One, which is, you would think that closest approach is the thing that you want to measure most, which is that big spike. But it turns out that there are actually 2 other points that are really important as well, which is when it reaches its maximum velocity along the line of sight and its minimum velocity along the line of sight. So this sets up kind of an observing schedule that you need to do for that year, right? So you don't want to miss it in April. You don't want to miss it in May. You don't want to miss it in September. So you have to schedule your observing time in such a way that you can maximize the time on the telescope. So here is just a 3-dimensional orbit of it for for you to sort of see, which is so the start of so if we look at X and Y, this is if you just look at the sky, this is what what the star does. In January 2018, it was here. It's going to move all the way here in May, where it goes to the closest approach, and then at the end, the start of 2019, it would be here. So as it goes around the black hole, it actually whips by super fast. This plot shows the z distance, which is basically the line of sight distance. So if you think about if I were the supermassive black hole, then in 2018, basically the star is going to go behind me. And so most of its time is spending in front of the supermassive black hole, actually. So that's kind of like what it looks like in 3D, if you want to think about that way. And in fact, there's these two special points where basically it crosses the plane of the sky. So you can think of it like an oval that intersects the piece of paper that's the sky. It crosses at these 2 points. And it turns out that this is why it makes those 2 points extremely important. Okay. How do we actually observe this? So the way we do it is with this technology called adaptive optics. I really like this photograph because this is a photograph of the major observatories on top of Mauna Kea in Hawaii. So these two telescopes are the Keck Observatory. So the Keck Observatories have two telescopes. They're both 10 meters in diameter. And this is that silver one I showed you earlier, which is Subaru telescope. And off the screen where the laser ends, it's a Gemini Observatory, which is another 8-meter telescope. So what are these lasers doing? So it looks like we're building a Death Star, but it's not. But these lasers are basically orange because they're sodium. They're tuned to the wavelength of sodium, and they're all pointed at the very center of our galaxy. So if you were here, you would have no trouble finding the center of our galaxy because it turns out on this night, all 4 telescopes were looking at our galactic center. And so you get this really cool image. Why do we need the lasers? Okay, to explain that, let's step back. As you guys are all observers, you know very well that the atmosphere makes stars blurry, essentially. So if we take pictures of the galactic center of our galaxy, with an infrared light, and we take images that are 0.1 second apart and play it back, this is what you get. So basically the atmosphere sort of shifts the stars around, kind of like looking at pebbles on the bottom of a pond. And we call these speckles because these little dots that sort of dance around. And so if you think about a long time, like elapsed image, what happens is these speckles sort of make all your pictures of the stars blurry. To get rid of, so this is kind of what the galactic center would look like if you take a long exposure image. But what we would like, if you turn on adaptive optics, which is a technology which basically corrects the blurring of the atmosphere, this is what you see. By the way, to give you a sense of the scale of this image, so this image, by the way, in physical size is about 0.5 parsecs, which is a pretty small scale astronomically, but this scale is very tiny also in angular size of the sky. So this whole image, if you take one of your hairs and you put it at arm's length, the hair would cover more than this whole image. And the part of the image that we're most interested in is this very, very tiny part in the middle. And this is the star SO2 that we are trying to watch or going to the black hole. Okay, so how does adaptive optics work? So the way adaptive optics work is that the light goes from the sky into this, what we call a deformable mirror. And then this light then bounces into a mirror that splits the light into 2 different components. So basically it sends all the optical light into this system, which is what we call a wavefront sensor. It senses how distorted the light is. And then it sends all the infrared light to our science camera because we want to capture the light in the infrared for our stars. And so the way this kind of works is that you can think of this mirror as like a funhouse mirror. So you know how like in a funhouse mirror, your image is all distorted, right? So that's what kind of like what the atmosphere does. But think about if you had another funhouse mirror that's exactly the opposite shape of the one that distorted you. So that means that you can undistort an image. And so this is the way these mirrors work, is that the shape of the mirror changes thousands of times per second to undistort everything that the atmosphere does. And so that you get a clear image. So this is kind of an illustration. So without AO, you get an image that looks like this. And when AO turns on, you get an image like this. It turns out that, so this is one of the test AO images for an observatory called Lake Observatory. But you can see how like this fuzzy blob actually turns out to be 2 stars. And so really with these kind of adaptive optics technology, you can really take advantage of these large mirror telescopes we have on Earth. Okay. One of the caveats, though, for adaptive optics is that you need a reference star, meaning that you need to know how the atmosphere is distorting, right? I said that you needed light from a star to see the distortion. So it turns out you need a star that's pretty bright, actually, to be in order to follow the distortion of that star so you can undo the distortion. But the center of our galaxy, while it has many, many stars in the infrared, most of the galaxy is actually in optical light is blocked by all the dust between us and the center of our galaxy. So it turns out there are actually not very many bright stars in the atmosphere in near the galactic center for us to look at for adaptive optics. And so what do? It turns out that you can create your own star with a laser. And this is kind of a serendipitous thing that happens, which is that about 90 kilometers up in the atmosphere, because of deposits by micrometeorites, there's actually a layer of sodium atoms. So there's this in the atmosphere. It's a very, very thin layer, and it keeps getting replenished by micrometeorites. And so if you tune a laser to the same frequency as sodium, you can get the very top layer of the atmosphere to light up. And so you can use that light as a star itself. And so that's what we saw in that image of all those lasers. That's why there's all those lasers, and that's why they're orange, is because the sodium wavelength that we use is it's orange to our eyes. So here's the 2 Keck telescopes again, and they're making this little spot up in the atmosphere. And we call this laser guide star adaptive optics. Okay, so that's the technology. But we actually need to make the observations itself. And so here is our first observation in 2018. We were super excited about this. This was in March. And so I'm gonna show, this is sort of like our vacation slideshow, but of all the hard work we had to do in 2018. So this is our very first observation in 2018. This is Professor Andrea Ghez. This is Anna Churlo, who's a research scientist. This is Devin Chu, who is a postdoc, and this is me. So this was our night of observing. We thought everything was going great, but as you all know, the weather does not need to cooperate. And often it doesn't. And it turns out, actually, 2018 was one of the worst weather years ever on Mauna Kea. And it was so bad, people couldn't be on the summit because of the snow. There was so much snow. And so we thought we were going to miss the closest approach. And actually, and then we were lucky because there were a couple nights that we could get. And then not only that, so now we're in May. This is what we captured on our webcams from the mountain on one of the nights, which is that, as you guys might know, Hawaii has volcanoes. Luckily, the volcano that Keck is on is fairly dormant, so we don't have to worry about that. But Kilauea, which is one of the most active volcanoes on Earth, is definitely active. And in 2018, there was a very large eruption, which is like this here. And you can see it blow out through the clouds. It doesn't really affect the our telescope very much, but the problem with volcanoes is that they release a lot of sulfur in the air, and you when it mixes with humidity in the air, it becomes sulfur dioxide basically. So it becomes like sulfuric acid, and so you can't open the telescope because then it would just burn off the layers on your telescope. And so we needed to wait until the sulfuric acid fumes sort of like dissipate enough for us to actually find observing. But luckily, miraculously, we did get to observe closest approach in June after all. We had many, many nights that year because we were wanted to be sure, and we definitely needed them. Okay, so this was our closest approach. And then this is us in July observing the minimum. So these are all grad students at the time. And so it takes a big group of people to do all these observing over all this time. So Rebecca to tell you all about it. She's an expert at it too. Okay, so now we've finished observing in 2018. But we need to put it together with all 24 years of data, right? You can't just take the data from 2018 because you are trying to measure a very small difference between what the orbit should be predicted by Kepler versus what should be predicted by general relativity. And so I'm going to show you now this video, which is real data that's taken at Keck over time. So it's kind of like a stop motion video basically. So this video when I start this, you'll see images across time. So this is 1995, and so you'll see here. All right, so what you're seeing is very sped up all of our images that we've taken at the Galactic Center, and so you can see that all the stars are moving, right? So okay, we're going to draw an orbit here to make it easier to see. So there's the black hole is actually here, where my mouse is. I don't know if you can see this now. Yeah, here you go. So look carefully at that spot. Do you see how it blinks, by the way? I don't know if you can see this well in your video, but the reason the black hole blinks is because stuff keeps falling into it. And so it glows before it hits the event horizon. And so you see the black hole flicker all the time, actually. It flickers at lots of time scales, even on the order of like 10 seconds during the night. And this is on the order of years. So it has large scale fluctuation. But anyway, so this is the data that we have taken over around 24 years or so. Okay. One thing you might ask, looking at this video, is all the stars move, right? So how do you actually put them together in a common coordinate system? Because you need to basically align everything so that you know how the stars are moving. But if there's no common reference source, how do you do it? And this is actually one of the central problems in our work that we struggle with all the time. And that's because measuring the coordinate system is really important in order to make the measurements of these orbits. And long story short, though, we use these stars. They're called radio masers, and they're just special stars that are both bright in our infrared wavelengths, but they're also bright at radio wavelengths. And the reason it's bright in radio is really important is because you can measure these stars in the radio with respect to background objects like external quasars and galaxies that don't move in the sky. So they kind of make like a grid of fixed points in the sky. And we would love if we could do that in the infrared, but unfortunately there's just too much stuff in the way in the infrared where we make our observations to see things like quasars in the background. And so we kind of bootstrap off the radio observations of these stars into the infrared. And then we use these stars, their measurements in the radio, and then we use their measurements in infrared as kind of like a grid to put all the stars on. Okay, so those everything I showed you right there were what we call astrometry, which is the motions of the stars in 2D basically. But I started out this talk with talking about redshift, right? Which is the motion along the line of sight, moving away or towards you, the star. And so how do we measure that? And the way we do this is with spectroscopy. So here's me standing in front of the spectrograph that we use. This is at Keck. And so the telescope is actually like over here somewhere. And the spectrograph is sort of like human sized. And it actually sits on a platform on the side. So Keck is what's called Naismith mounted telescope. So the instruments don't move with the telescope. There's basically a tertiary mirror that's basically directs the light onto this platform where the instrument is. And the reason that like we do it this way is that if you mount instruments on a telescope, the flexure from just gravity of it moving around will make the instrument basically unstable over time. And so with this kind of work, you need the most stability that you can because you want like 24 years of stability kind of. So what we use is the spectrograph. What's cool about the spectrograph compared to the traditional spectrograph, it's called integral field spectrograph because it takes basically like a 3D image. So that means like, let's say this is a galaxy, you can see the whole galaxy, but then it also takes basically these images at 1400 wavelengths. And so you get a three-dimensional cube basically. And so if you look down this direction, you'll get a spectrum, meaning you'll get how much light that star is emitting at different wavelengths. Okay. And so here it's just a screenshot of what we see at night at the telescope, actually, of the Galactic Center. And this little dot here, it may be hard to see, is the star SO2, by the way. Every one of these dots are a star at the center of our galaxy. And this is basically a 2D version of it, but then if you basically think about taking a straw through this, then you can extract the spectrum. And so here are some extracted spectra of stars around here. I'll show you SO2 spectrum next, but these are other stars in the galactic center. And so here's wavelength, and then here's on the y-axis is flux. So basically, you can see like these dips. Do you see these dips? These dips are caused by atoms on the surface of the star absorbing light. And so that's how we know what the compositions of these stars are. So for example, we can see like these are sodium lines. This is titanium lines. There's some silicate lines here. And Brachia Gamma, this is hydrogen. So these stars are hydrogen. Okay. So these stars actually are really different from each other. And in fact, we need to model this effect in order to really measure the star well. And so what we do is we use what's called a physical model of the atmosphere of the star. So here is an artist's conception of maybe what SO2 might look like. We don't actually know what the surface looks like. It just looks like a point for us. But effectively what happens is that a lot of things affect the spectrum that you see. One of the biggest effect is temperature of the surface. And then also the gravity. The surface gravity of the star itself, the elemental composition, as you might imagine, affects what we see of the spectral lines. How fast the star rotates is important, and then the parameter that we really want for this work we call radial velocity, which is just the Doppler shift that we were just talking about. So how fast the star is moving, or basically how red shifted or blue shifted the spectra are. And so let's look at SO2. So we're now zooming in around the hydrogen line around SO2. So here's what in orange is what we get for SO2 in 2018. And then in blue is our best fit model. There's this little dip here, and this is actually a helium component in the star itself. So we see a lot of hydrogen and helium in the star because SO2 is actually really, really hot. It's about it's close to 30,000 Kelvin in temperature compared to our sun, which is more like 5,800 Kelvin. Okay, This is what it looks like if you put all the spectra together. Normally, like you would, the motions of stars are fairly subtle and not easy to see by eye, but SO2 moves so fast that you can see this line change really fast, right? Like you can just tell that where it's going. But basically, in 2018, or it's sort of going backwards in time. So in 2017, it was here. It was moving at 2,000 kilometers per second compared to rest velocity. And then it moved up to sort of 4,000 kilometers per second, and then it goes back down. By the way, if you combine this velocity, the line of sight velocity, and then what velocity we measure from the plane, the sky motion, SO2 moves close to 3% the speed of light in 2018. So the star is really hauling. And it has really strong effects. So actually, special relativity also is an important effect that we have to take into consideration. Okay, so how do we measure it? So the way we measure the gravitational redshift actually we have to break it down into the different components. And so radial velocity, here's what we actually measured. But there's a component which is the offset, which is just how fast the solar system is moving with respect to the black hole around the galaxy, right? And then the second part is the Keplerian orbit. So just without general relativity, how fast would the star move? And then there's two components that actually is in relativity. There's special relativity, which is what happens when things travel really fast. Like I said, SO2 is traveling at like 3% speed of light. And general relativity, because SO2 is traveling really close to the black hole. And here is where you have to have this M here. This is the mass of the black hole. And so that affects how much it impacts the star's velocity. And so we have this parameter here that basically, this is what we're trying to measure, which is how much is this redshift of the star. Okay, so here's our measurements all put together now of the 24 years together. Here's, so this is X and Y. So basically, if you took a photograph of the sky over many years, you'll see that the star kind of moves along in this sort of ellipse. And then this is the radial velocity. So the velocity along the line of sight. And here, over here is 2018. You can see like we're in 2022, this was our first closest approach. And in early 2000s, we were just testing the spectrographs at Keck. So we didn't have we didn't know enough of the orbit actually that the SO2 was going through closest approach, but we also didn't have enough of the instrument like completed to get very many data points. And so this is why the density of points is so low over here compared to over here. All right. Okay, so how do we do this test of general relativity? So the way we often do this is what we call model selection. So in this one, technically this is Bayesian model selection, but it doesn't matter. What matters here is that typically when we're trying to test between different models, we want to ask, what is the probability of getting our data, which is what we call X is here, given the model, right? And then you have to test between different models. So for us, what we're doing is we're testing that how likely we're able to see these data points given the general relativistic model compared to the likelihood of getting these data points given the Newtonian model. So essentially asking, is Einstein more correct than Newton? And this is a logarithm of 10. So in sort of more easily understandable terms, we can translate this into words to say that the general relativity is 43,000 times more likely than Newtonian to explain the observations. So essentially, it is extremely unlikely that Newton is the right model for this star. It's much, much more likely that general relativity works. Okay, that's great. So, but let's go back to originally, remember when I said what the gravitational redshift we expect to see is? So this here is the x-axis is time again, and then the y-axis is the deviation from Newtonian. Remember I said that if general relativity is right, we should see the star moving faster away from us than we would expect, right? And in fact, theoretically, it should move faster by about 200 kilometers per second. And so if you look at our data points and the GR model, which is this dashed line, it falls right in line with that. So this is like beautiful agreement between general relativity and what we expect. And if general relativity was wrong, by the way, if like Newton was right, you would expect everything to be down at 0. Okay. The other way we can talk about it is this this factor, this redshift factor that we have. So general relativity for this redshift factor we expect to be 1, and then Newton would be 0. And so this is a probability distribution of this this parameter. And so it's basically consistent with general relativity. If it's not 1 though, general relativity would not be consistent. Okay. So finally, then, what does this tell us about the nature of gravity around supermassive black holes? I would say, you know, Einstein appears right for now, at least for this redshift test. Not only do we get the measurement of the redshift, we can also measure the black hole mass extremely precisely, because we needed to know the black hole mass really well, right, in order to measure the general relativity in the first place. So in this measurement, we have the black hole mass pretty close to 4 million solar masses with these very tiny error bars. So these error bars, by the way, sort of are pretty extraordinary because they're below 1%. I don't even know my weight to below 1%, really. And so we can measure a supermassive black hole mass at, you know, 26,000 light years away to better than 1%. We can also measure the distance to the galactic center to better than 1%. So it's about 8,000 parsecs away from us as well. Okay. What else could we learn from these orbits? The next thing that we look at is if you look at the orbit animation that we show, it seems like the orbit is coming back to the same place, right? But we know that with general relativity that orbits, when they're really close to a strong gravitational force, actually does something called precession, which means that it doesn't quite end where it starts. So this is a cartoon of the precession of Mercury, which was one of the very first tests of general relativity, actually, on Earth. And so we know that Mercury precesses since ancient times. We've known this, but no one's been able to explain it until Einstein was able to predict it with general relativity. And the same thing happens to the orbit of SO2. There is a bit of a complication, though, because SO2 might not be alone, right? Because there's all those other stars. So there's something we call extended mass, possibly, which is that there are kind of unseen mass around the black hole, which is not the black hole. So there's this sort of fuzzy blue stuff visualized here. So, for example, the galactic center, because it's the center of the gravitational potential of the lots of things sort of sink to the center of a galaxy. So for example, like neutron stars, white dwarfs, stellar mass black holes, like small black holes, they sort of collect together. And so by measuring the relative amount of precession, you can also place limits on the extended mass. One of the tricky things, though, is that both extended mass like this and the black hole makes the orbit precess. So black hole actually causes the orbit to precess in one direction, and then the extended mass causes the orbits to precess the other direction. So it turns out with just one star, it's very hard to decouple all of these. And so what we're doing right now is to use multiple stars so that you can, because multiple stars will have different distances as they orbit around the black hole. And so they'll feel different amounts of mass. Okay. But I'd like to jump to my second question, which is, are the fundamental constants of nature really constant? Before I do that, though, were there any quick questions about what I've just talked about?
Shoot the mic.
Obviously, using my SO2 is running through material near the black hole. And so from one year to the other, or one close orbit, one perihelion basically to another, that orbit's going to move. And do we know how much it's going to move, since we've only really seen it go around once? So I'm assuming we don't have a real good grasp of how stable that orbit is.
So we've seen it go around twice because because we have in 2002 we saw it go once, and then now we see it again. And so that's what allows us to see this precession, actually, to see it like kind of turn. And so yeah, so the we know it's stable within the time scale that we've measured, but that doesn't guarantee that, 30 years from now another star might get close enough to change its orbit. And in fact, that's one of the interesting questions at the galactic center, because the galactic center is extremely dense. The ground stars will actually meet each other. So on average, in fact, stars will fall into the black hole too. So the galactic center has a stellar density of something of greater than 1 million solar masses per cubic parsec. So it's kind of wild to think about. So the closest star to the sun is Alpha Centauri, which is about 4 light years away. If we were at the galactic center, that volume would instead have 1 million stars in between us and Alpha Centauri. That's kind of like the very different environment. And so we do look to see if any of these stars, during their orbit, if they sort of jump, that could indicate interactions. For SO2, though, so one of the interesting about SO2 is it's actually a very massive star. It's probably about 17 times the mass of our sun. So it takes a lot of stuff to move the orbit of SO2. So if it's just gas and dust and stuff, like that won't affect the orbit at all.
But there's a lot of it around there as it goes around.
We know that the density of dust and gas, because we can actually detect how much dust and gas is in that environment. It turns out that it's actually really little. So if you take all the dust and gas around SO2 and you add it all up, it's less mass than the moon.
Oh, okay. All right. So it's really not.
Yeah, so it's like really spread out and not
Okay.
so much.
All right. That was basically my question, is how homogeneous the stuff was and how thick it was. Okay, thanks.
Sure.
I have a quick question. How long do you anticipate being able to continue measuring SO2 before it enters the black hole?
Oh, based on our current models, SO2 will never fall into the black hole unless another star passes by and pushes it in, essentially. So just like how the Earth is very unlikely ever to fall into the sun, the angular momentum of the orbit basically prevents that. But that doesn't mean other stars might not fall into the black hole. Based on the stellar density of that region, we think that a star falls into a black hole about once every 100,000 years. So it could happen.
So in that video you were showing us earlier, where we kind of saw some blinking within just the short years of the measurement, those weren't stars falling in. That was probably
No, those if a star fell in, like it would be super, super bright. Like
Okay.
we would it would definitely make the news.
So so that blinking was just what the dust in the area then maybe?
Yeah, exactly. So they're kind of like little asteroid-sized pellets that are falling in is kind of how I think about it. So it's
Okay.
I think of it like rain. It's like stuff is raining on the black hole all the time, and then
Mhm.
it sort of like flares up because of the as the stuff sort of spirals in, it heats up and interacts with the magnetic field of black hole and stuff like that, and then so it releases a lot of energy.
Okay, thank you.
Sure.
Any other questions? Alrighty.
Okay. This might seem a totally different topic, but I promise you it is related, which is are the fundamental constants of nature really constant? So um, one of the really interesting things about physics is that we think that there are some numbers in physics that are just the way it is. Like they're kind of arbitrary. And things like the speed of light, I don't know if you ever wonder, like, why is the speed of light the way that is, why is the mass of the electron exactly that mass? Um, and so there are there's various thoughts about this. Um, Parts of it is that um, if the if Einstein is right about the universe, there's a principle called local positional invariance, or it's called Einstein's equivalence principle, meaning that the laws of nature are same everywhere in space and time. That means that if we can measure the speed of light on Earth, that should be the same as the speed of light next to a black hole. That should be the same as the speed of light at the Big Bang, right? Um, but how do we know this? You know, there's how do we measure the speed of light at the Big Bang? So there's this kind of interesting question about the our fundamental assumptions in physics, right? And in fact, many models that are extensions of our current models, so for example, like quantum gravity, unification theories, a bunch of dark matter and dark energy models predict a violation of Einstein's equivalence principle. So it would predict that maybe the fundamental constants might not be fundamental at all. Um, and in fact, these kind of unification theories posit that there is a bigger reason why the speed of light is the way it is. And it's related to some other property of the universe that we haven't discovered yet. Okay. And then the last one is more philosophical, which is that the reason we can even exist to ask these questions is because the fundamental constants are the way they are. Because they govern everything about the way atoms work in the universe, right? And so the fact that stars make a lot of the elements due to fusion has to do with a lot of the fundamental constants. Okay. So the fundamental constant I'm most interested in studying is something called the fine structure constant. And the reason that this is a really interesting constant to study astrophysically is because the fine structure constant governs tons of processes, including atomic transitions. So meaning that when you have an atom, there's all these electrons in the atom, right? And we know that the electrons have energy levels in an atom. So when the electrons jump between energy levels, it emits a photon, so light. And so we can detect the light. In fact, that's those spectra that I showed you, right? That's why we see those dips, is because these electrons can also absorb that light as well. And so they're discrete jumps. But why do those electrons have that energy jump? Has to do with this thing called the fine structure constant. And the fine structure constant actually is made up of 4 different constants of physics. The electric charge, this E eta of 0 is it's an electromagnetic constant. This h bar is Planck's constant. It governs things on quantum scales, basically. And then c is the speed of light. And so shorthand, you can remember Fine-Structure constant, which we call alpha, is like 1/137. So what's cool about this constant is that you can test variations of this constant by measuring spectroscopy. So basically measuring how those atomic lines look in space compared to what you see on Earth. But that's how we're going to be able to see if the Fine-Structure constant is the same everywhere in space, right? Because you can take stars at different locations in the universe and say, aha, do the sodium lines and the hydrogen lines, do they still stay at the same place, right? Because if they are, then that means the electron transitions are the same energies, and therefore the Fine-Structure constants are the same. Okay, so what's kind of interesting is that astrophysical tests of quasars and white dwarfs have found maybe signs that the Fine-Structure constant might vary. And the way, let me explain this a little bit. So a quasar is basically a supermassive black hole that's really, really far away, but it's much, much brighter than our black hole, right? And so it's sort of like like a lighthouse. And the light from these quasars will pass through lots of gas along the way to us. And they are so far away that they actually can probe large portions of cosmic time. So basically these quasars are, some of them are 10 billion light years away. So you can kind of probe how much the Fine-Structure constant might have evolved over the history of the universe by looking at quasars from different distances away from us. And there's this measurement, which is still fairly controversial in astrophysics, which is that the Fine-Structure constant might vary on the scale of 1 part in 10,000 or so in the distant past compared to today. So not everyone agrees about this, but it's kind of an interesting aspect of maybe new physics. Okay, the other one that is closer to kind of what we can measure is that if there's an experiment that was looking at white dwarfs, the surfaces of white dwarfs. So white dwarfs are stars they're basically the cores of stars. And so they're very, very compact and very dense. That means that the surface of the white dwarf it has really pretty strong gravity. And so there was this measurement in 2021 that found that basically iron lines, spectroscopic lines of iron, seems to show that there's a variation once again in about some like 6 times 10 to the minus 5. So around again an order of part in the 10 to the a part in 10,000 or so. And so this one suggests that maybe gravity has to do with has changes in the Fine-Structure constant. And so what we are trying to do at the Galactic Center is ask this question: can we measure variations in the Fine-Structure constant around a supermassive black hole? And what's nice is we have tons of stars at the center of our galaxy due to this. And they're also at various different distances around the black hole, right? And so that means that they should show different variations depending on how far they are, if gravity is really the thing that's causing this variation. Sagittarius star, by the way, is the name of our black hole. So the way we do this is we look for the changes in the position of the spectral line compared to its rest wavelength. And then more complicated because we know, remember, that the position of the spectral lines depend on both general relativity and then the velocity of the star. But we can basically measure this by measuring the orbits, and then we can look at this quantity by measuring how different atomic lines compare to each other. And so this is a new experiment that I've been working on, which is to actually now measure. So this spectrum, do you see how there's like way more lines than the spectrum SO2 I was showing you earlier? And that's because this is a different spectrograph. So this spectrograph has what we call high spectral resolution, meaning it can measure very small changes in wavelength. And so we can get tons of these lines. In fact, you can see like, I don't know, your screen might not be so good to see like there's an iron line, this is a silicon line, there are a lot of molecular lines here. This is scandium, sodium here again. And some of these lines are really sensitive to variations in the fine structure constant. Because it turns out, just due to quantum mechanics, certain transitions have high sensitivity to fine structure constant and certain ones don't. Unfortunately, hydrogen and helium don't have very many lines that are sensitive to the fine structure constant. So actually, we need metal lines from cooler stars and SO2 for this experiment. Okay, so what were we concluding about this? So we find here that so we're using about 5 stars, and we find that actually we don't see a variation. So we are sensitive to about a part in 10,000 or so now, and we still don't really see variations. So here is once again like that plot that I was showing you earlier, which is like the mass of the object versus the gravitational potential. So on Earth, we've tested variations of fine structure constant really, really precisely. And it's down here. So this is that white dwarf experiment I was talking about. And then here is the stars that we're doing at the Galactic Center. So we want to push this further in order to improve it. But I think this is a really promising way of trying to get better limits on some of these fundamental questions. Okay, so I know I'm running out of time, so I'm gonna talk just a little briefly about what is the future of the Galactic Center kind of experiments. So I'm gonna show you a video, which is a simulation of what our improvement in technologies will get us. So on the left here is our current adaptive optics. In the middle is what's called next generation adaptive optics at Keck, which is coming online in the next 2 years or so. And then in the right is TMT, which is a 30-meter telescope. So this is a new telescope that we want to build, which is 30 meters in diameter, so much larger than Keck today. And that telescope will really revolutionize things. And so in this video, basically, I am simulating all the stars that we know of at the Galactic Center, and then also a population of stars I think that are there, but below our detection threshold today. And so here is what it kind of looks like over time. You can see these stars are orbiting. So we should be able to see them more distinctly here. And then really when you go to the 30-meter telescopes, you can see how much better you get. And the reason things are so much better with larger diameter telescopes is that you can just get better and better angular resolution. So you get much, much sharper images. And so you can see all the stars that are going around the black hole that you can't see today. I told you how like SO2 goes around the black hole in 16 years, right? I think that with TMT, we're going to be able to see stars that are going around the black hole in just kind of like 3 years. So a lot of the experiments I was talking about today, instead of these like multi-decade long experiments, will be kind of experiments within like a grad student timescale that can be done. All right, that's it for my talk. I'm happy to take any questions.
Pat, grab that microphone. Sure. Anybody have questions for Dr. Tuan?
I have one. Is it on?
I think so.
Okay. Can you hear me? Okay. The 30-meter telescope, that's going to be on Earth. That's not going to be in space.
That's going to be on Earth, yes.
And where is in Hawaii or?
Yeah, so that's the ideal location for it would be in Hawaii.
And I'm sorry, I didn't understand why you'd be able to see more with the 30-meter telescope instead of waiting for the how many years was it? The rotation that we were seeing for SO2, you said you'd see it much more rapidly. Why was that? With the 30-meter?
Oh, it's because we can see stars closer to the black hole.
So there'll
So
be different stars we'd be looking at
exactly, yeah, yeah. So
that
we'll be
just
looking
aren't
at
showing up.
fainter stars and stars closer. So today, SO2 basically is this really bright thing here,
Mhm.
but underneath we know that there's lots of stars that are below the sensitivity that we can detect today.
Got it. Thank you. You have a question. Okay.
Gina?
Thank you.
For SO2, how large of a mass would a star would need to actually be there to move it off that 16-year orbit? Or is there any stars that we can even see yet before using the TMT much of this star might interfere?
Yeah, so that's a good question. So we're always trying to look for stars that are even closer if we can. And the reason why we don't have a complete census of stars yet is you can kind of see from this. This is like on the left side, this is real data, right? So this is like the stars kind of cross each other in projection a lot. And so when they do, we can't see the stuff that's like they're blocking essentially. And so sometimes, until they move away, right? And so each year, actually, we discover more and more stars in this region as stars kind of like move in and out. And so we might discover some stars that are closer that could affect things. We kind of know that there isn't really a star close enough that can affect SO2 enough, like within the region that we've surveyed so far. That doesn't mean that there couldn't be in the future. And by the way, it's not just stars that can move SO2. It could be other black holes as well. That could be much more massive than SO2 itself. So that could shove SO2 pretty easily if they come in. And smaller black holes, like say a black hole like 40 times the mass of our sun. That's small compared to the 4 million, but big compared to SO2. And so that could knock its orbit around.
Thank you.
Gina, you're like me. I just want to see a star get nudged into the black hole, right?
I would love to too.
Wow, excellent, excellent presentation. I mean, we went from the galactic center to the energy transition of electrons to quasars and white dwarfs. I mean, we've covered it all in the universe, haven't we? Dr. Tuan, I think you're a master at your subject, and it clearly shows in your presentation. So let's give him a big round of applause again.
Thank you. It's really great to briefly see you all, and hopefully we will meet in the future in person.
We look forward to that. Thank you very much. And Rebecca, will you please stay on for just a moment?
See you guys later.
Thank you, Doctor. Yeah. Okay, we're going to transition now to the little bit of business we have to do. And that's the installation of the 2025 Executive Committee officers. So Eric will change the slide here. And I said this last year, the Executive Committee sounds like a bunch of guys sitting around a table smoking cigars and making executive decisions, right? But it is totally not that way. These guys are the hardest working group, guys and girls. Month to month, week in and week out, they're just doing the nitty gritty business of the club, the finances, the setting up of programs, the setting up of star parties, all the organization, the future events. So I'm just so pleased to work with this group. They're so capable. The ideas that float around, and we get great new topics to cover. It's just really interesting. I just really enjoy working with this group. It's a lot of work, but you all members that pay your dues, you're getting your money's worth. Let me tell you, out of these guys and girls, that newsletter that comes out every month, and you may not even read it, but it's in your inbox. Open it up and look how much content there is in that newsletter. Rebecca puts out an excellent newsletter. It's so topical, always good topics and content in there. So, okay, so there you can see us. I'll be your president, and looking forward to this. Will be my 3rd year serving as president of the society. Serving with me will be Eric Holland as secretary. Doug Christensen, right over here, will be the vice president. And Doug's my guy where I ask him for advice. Well, that's the vice and president, right? You ask him, he should be well, that's what I learned is that, yeah, it's not advice, it's the vices that Doug majors in. So Jerry has been our treasurer, and he does so much more. He's like the club historian and so many other things to do with. And Jerry, thank you so much for serving all these years. You did an excellent job. Rebecca, as far away as you are and remotely as you are, you always stay in contact. Always get that newsletter out. You're such a valuable part. Don't ever leave, even after you get your doctorate. We want you to stay, okay?
Thank you. I'm 10 years in.
Excellent.
Didn't Trevor say I should beat 21 before I retire from this?
Well, as I learned, you don't really age out of these positions. You just kind of grow into them. Yeah. 2 new members of the executive committee, members at large, Omo Alzula. Did I pronounce that right? Alzula. Stumble over your name, Omar, pardon me, and Patrick Lehman. So thank you guys for joining, and want to welcome you into the executive committee. So let's give these officers a round of applause. And a special thanks to Mark Gibbons for serving as member at large this last year, and Michael Chapman as well. So. Okay, just a few announcements, and then we've got the raffle prizes. So we'll get on with this. Our normal upcoming events. The 25th will be out at Highway 4 or Campo Seco. You know, we've been alternating low altitude sites depending on where the group wants to go. It also coincides with our high altitude start party. So stay in touch with the Google group to see where we're going and on that night, because we've got all of our options open. January 31st is a Friday night. We go back to Delta College. We haven't been there in a few months because they've been on break, but Delta College is a great place to come out. Even if you don't bring your telescope, come out and hang out with the members of the club. The Delta students are really a really interesting group to talk to. A lot of young aspiring astronomers in that group. And it's so easy. It's right in the middle of town, right at Delta College in the parking lot there. February 1st, we're back at Astronomy in the Park at Oak Grove. That's always fun. The people that come out there are always so amazed at what you can show them through the eyepiece. I mean, it could be something as mundane as a first quarter moon, but the amazing views that you give them through your telescope, really, it's kind of rewarding. It's really a lot of fun to talk with the public out there and engage with them. Okay, we've got 2 STEM events coming up. It's February 8th, and I'm going to jump down here to February 22nd. Also, February 8th is here at San Joaquin County Office of Ed. It's their STEAM event. And what this is it's where the science fairs from all the different schools, the winners of those science fairs all graduate to the next level, and that's this STEAM event. So they're all getting judged. The students and their families all come out. And so we usually set up a solar scope in the parking lot and then a table in the inside where the other exhibitors are. And so it's really a great event to talk with the public and to share our passion for astronomy. Yeah, show of hands, who's planning on coming to the STEAM event on February 8th? Yeah, good. Yeah, okay. February 13th, we're back in this room for a presentation by Dr. Aparna Vigakinson from USF. Eric's arranged for that presentation. Eric, her subject matter is going to be?
I believe she's going to be discussing the growing problem of satellites in orbit. And
We can all get behind the light pollution thing, right? Satellites. Okay, and then February 22nd, we're at our low altitude site. So a lot of good events coming up in the next couple of months. And then just a sneak peek, I didn't put it on the calendar here, but we have a lunar eclipse coming up. You remember what the date is, Jeff? In March? He's going to look it up. Yeah, I wanted to make sure you. Okay. So I think we've got a. Okay. March 13th and 14th.
Evening of the 13th, morning of the 14th.
Very good.
It's a good eclipse.
Look forward to that. We'll be talking about that before it comes. So, okay, we've got a couple of slides to share with you just for fun. If you guys are on social media or on the internet at all, you know, there's all kinds of photographs and all kinds of stuff going on, right? So it's so hard to tell what's real and what's fake anymore with AI. It's just really difficult. So I don't know if any of you spotted the problem with this. Maybe there's not a problem in your mind, but
Yeah, Pluto's not a planet.
yeah, Pluto's not a planet. Everybody knows that, right, Pat? Yeah. So if you go to the next one, Eric.
you've conveniently blurred your source here too.
Yeah, that's right. Okay. So you laugh.
It
But-
might be about the right size.
Okay.
Angular size might be
Okay.
appropriate.
Yeah, not counting for the difference in brightness. I've researched this and talked with Doug. We verified this is actually accurate. The size of the moon is about half a degree. The size of Andromeda, M31, is about 3 degrees. So it's about 6 times as big as the moon is. So it's hard to imagine, but this is actually true. Now, it's not as bright. That's why you don't see them in the sky like that, right? So, okay, and then next one, Eric, please. You tell me. You all recognize the mountain, right? El Capitan. Do you think you could see M31 and El Capitan at the same time like that?
Yeah. We're north looking south. Yeah.
I'm not sure about the orientation in the sky. That could be correct. It could be right.
Yeah. So I'm just thinking, could Andromeda be in that position?
Yeah.
Well, we're west looking east there, so I think so. Okay. All right.
Okay, so it's plausible, okay? So as I researched the credits and so forth, read all the different comments, turns out what this is a mosaic where somebody took the picture of the foreground mountain and then spliced it in with a multi-stacked image of Andromeda and spliced them two together. Yeah, so I guess it's real, but conjured up or created. So
What is this one? M33? Yeah.
seems kind of far away, but.
Yeah, it does.
Mhm. Okay, I think that's all I have. Again, there's the items from Neil Lark over there if you'd like to help yourself. Doug has t-shirts for sale if you've ordered one and not purchased it yet. Yeah. not Doug. I believe that's just about it. I'm going to turn the raffle over to. Did everybody get a raffle ticket? Okay. Then our. You only get one, Dennis. Okay.
No, I'm gonna prove somebody else no.
No?
Oh.
Yeah, Rebecca did.
I didn't get a raffle ticket.
Well,
I heard.
I'm sorry you have to be present to win, Rebecca. So I'm going to turn the microphone over to Pat and Omar. They're going to conduct the raffle, and keep your fingers crossed and good luck to everyone.
And just so you know, Omar and I laid everything out. So what we're gonna do is pull a ticket and we're just gonna go and order down this. And just so you know, all the tickets in there are Omar's and mine. So not that we stacked the deck at all, but
I want to get electric outlets.
what's that? Yeah.
The electric outlets.
Oh, yeah. Oh, wait a minute. Was this one of our items as well?
Yeah.
Oh. Well, this is the first one then. The number ending 4672. That's mine.
Now we'll take a turn for the delicious. We have some astronaut ice cream here. We got a few of these sprinkled throughout. Do they have sprinkles? Okay, so it's a vanilla ice cream sandwich. The first one goes to you. I don't like it. You're good on it. All right. It ends 681.
That's me.
There you go.
See, we didn't need dessert really. Let's see. The next one, and this is our Starbucks gift card.
That's my friend.
It ends in 687.
That would be.
All right, next is the one I'm hoping for. The observer sauce. Don't go out without them. Observing sauce. So we go. 683. Oh, nice. Congratulations.
Thank you.
Let's see, the next one. And this is, again, our astronaut ice cream for 675. I'll pass. You don't want your ice cream? Okay. Let's see, how about 679? Oh, there you go. We have a space the next time.
Yes. All right, the next item. This is a good one. It's the Observer's Handbook 2025. Current. The big one right here. It's the lucky person. All right, ticket that ends 668. All right. Yeah,
What, now we have another ice cream. And let's see if we magically pick Mike's number. Let's see here. 677. Okay. 677, is that you were on?
Oh, I think.
Oh, that's me. I'm taking this one, I go to the next time.
All right. All right, we got another good one here. The National Geographic Backyard Guide to the Night Sky. Full of a lot of nice information here, but you will need a magnifying glass to read it. All right. Okay. Ending 667. Oh, wow. All right. We got
FYI, those of you winning books, we expect a book report presentation.
This is really
You just have to do their
So
own
this is a
presentation.
laser pointer that was donated by Neil Martin's family. So something,
In a very nice case.
yeah, something actually sentimental and 690. Hey.
There you go.
Somebody let them know about safety.
Yeah.
That's your point that here.
All right, on to the next ice cream here. Here we go. All right. Where's the number? 669. 669.
Right here.
There you go. All right.
Yeah.
Lucky table over there.
The phone will go on. Tim will be the next guy.
So this is pretty cool. It's a calendar, the year of the sky calendar. So let's see. 685.
Wait, that is me.
You got it so close.
Ice cream. Here you go. 689.
Yeah, I
Got
still
another one,
got
okay.
Yeah.
Oh.
Here you go. Enjoy.
Thank you.
Popular science destination Mars. Okay. And the winner is 671. 671.
That's me.
Oh, yeah, how did we do that one? Pull that one out.
Okay, and we have an ice cream. Oh, yeah, same flavor. And it is 680.
That's me.
All right. You go.
Now you guys are on the way, right?
We don't want to see it on eBay or anything.
For left and right. Big piece, the biggest, heaviest thing we have on the cake. And the last one, 673. Ah, thank you. The guy who didn't win can arm wrestle with for life.
Your bad soul, that's the same thing.
No. Oh.
Excellent.
You know what? Put them in the trash.
Yeah. Thank you. Thank you, Pat and Omar. I think that's pretty much concludes our meeting for this evening. Just a couple more things, I think. If there's leftovers and you're willing to share them, there's some to-go containers. Charlotte, can I have a piece of lemon cake? Rebecca, thank you so much for setting up the presentation this evening. It was wonderful. It's great to have you. We look forward to seeing more of you this year. I know you're really working hard, but look forward to seeing you. And Joseph as well. So
Thank you so much. And thank you, Jerry, for the DoorDash gift card. We got Chinese.
Tell them not to click out there because I need to take a picture of the board.
Sorry, what?
Well, I mean,
yeah.
with you on this, we're gonna.
Yeah, you're not excused yet, Rebecca. So hang on just a moment. We're going to get a good picture here in just a moment. Yeah. Oh. Okay, so good attendance tonight, 25 in person and 4 on Zoom. So thank you, Jeff, for taking the census and keeping track of all that. Want to just thank everybody for coming tonight. Thank you for creating what is, I think, a wonderful group, a club. I think we got a great year ahead of us. Got a lot of good activities, a lot of good presentations. It's going to just be a fabulous year. We've got young folks coming into the club. We've got amateurs of all levels. So I think that this year is going to be a really good year. Not only that, we get to celebrate our 75th anniversary, right? And we're going to milk that one, I mean, all year long, right? I mean, I think we'll arrange to have a cake at every meeting. So just a reminder to come in person. Rebecca, we'll DoorDash you a piece of cake once in a while. Okay. I believe that's it. So again, I want to thank everyone for coming and enjoy the rest of your evening. Thank you.
Is it okay if I start recording?
Yeah. And then if I could have the